Well, good morning. This is 8:37. Sorry I'm 7 minutes late getting started, but I was grading a paper and lost track of time, and still no students were here. So anyway, this is Math 238, differential equations. We're in it's the 20th of June, 2019. Like I said, I'm the only one in the room. We're in Chapter 2, First Order Differential Equations, and 2.3 are linear equations. We got started on this last time, didn't quite finish. Let's continue. I have a fairly major announcement to make, but I want to wait till there's at least one person in the room to make it, because I don't know if anyone will hear it if I just make it on here. But that way I'll guarantee at least one person. I can't get the slide to open. Don't know why. Still not opening. This is acting strangely this morning. So what the problem is. Oh, here it comes. Finally it's there. Okay. Let me get my pen set up. All right. So, we talked about, and had gotten down to the point of saying, your integrating factor for these linear equations is a strange-looking equation called mu of x. They just choose to name it that. And that's defined to be e to the integral of p of x dx. Okay? Now, just to remind you, what's the standard form for these linear equations? Here's what they want it to be. dy dx plus p of x y is equal to some f of x, or g of x, f of x they call it. Different, it doesn't matter what you call it, something else. Okay, now, so find that coefficient function for your linear term, okay, the y term, integrate that, don't do a plus c, just integrate that, whatever that turns out being, that's e to the power, that's your u of x, okay? So that's your integrating factor. Just hang on to that, that concept, okay? Now, so what we're going to do is multiply both sides, every term on both sides of the equation by this integrating factor, okay? And that will give you mu of x, I'm sorry, let's not call it mu of x, let's put what it actually is. Sorry. That's e to the integral p of x dx times dy dx plus e to the integral of p of x dx times p of x times y is equal to e to the integral p of x dx times f of x. Okay. Now, seems like making it a lot worse. Okay? But let's think about this. What we have on this side is a function, e to the, that integrating function, that mu, e to the integral of p of x dx times dy dx plus y times the derivative of this thing, okay? Because the derivative of that thing is e to the integral, same thing, times the derivative of what's the exponent is, and derivative of an integral is the p of x. So sure enough, this has become the derivative, d by dx, of the product of e to the integral p of x dx times y. Okay? Because if you did this differentiation, you do the first times the derivative of the second, plus the second, which is your y times derivative of the first, and derivative of e to anything is e to that same thing. Then by chain rule, the derivative of the argument of e, or the exponent part of e, is the derivative of an integral, and that's just p of x dx. So yeah, that's right. And this is equal to e integral p of x dx times f of x. Okay, what you do is then write it as a differential. Take the dx out of there, integrate this, and integral of a perfect derivative is e to the integral p of x dx times y, okay, is equal to whatever that is, okay? Now, don't go around memorizing this. Don't try to do any, and then what you do is take this, whatever this integral is, e to the integral of p of x dx, f of x dx, divided by your e to the integral of p of x dx, okay? Because when you divide both sides, that disappears. There's your solution. Now, don't memorize that. Don't write that down. Don't say, this is what we do. Rather than hauling around the integral of p to the x dx, you integrate it, okay? You just integrate it. Then whatever you get, you put as the exponential, okay? As the argument of the exponential. And then, if you can, then you just continue the thing. It's the process that you do. Don't memorize the result. And they say that here. And somewhere out here, and they do it rather strangely. I would have done a plus c at the end here. They do it earlier at this step, and then when they divide the plus c by that too, which is rather strange, okay? But it's okay. It's perfectly correct. All right. So let's go back and do some steps here, okay? Do not try to memorize this thing. It's just showing you that's what your solution is. But, number one, that you have a solution, okay? So here are the steps. First, put the linear equation in standard form. Okay, now, that's abbreviated like crazy. What do I mean by that? Okay. And I would even say a step before this one, 0 step. They don't put this one in the book. Take a good long look at that equation. Make sure it's a linear equation. Okay? Back off even one more step. Look at that differential equation. See if it's separable. If it's separable, separate it, do it that way, okay? No reason to go through the agony of this if it's separable, okay? Let's assume it's not separable. Then make sure it's a linear equation, that the dy dx is not multiplied by anything, is raised to any power, okay? And make sure the y is not raised to any power, okay? And make sure the y isn't multiplied by dy dx, okay? Make sure it's a linear equation. Once you have that, and you're certain it is, then put it in standard form. Now, what does that mean? If you had a coefficient function with the dy dx, divide everything by it, okay? And that will then give you a p of x for your linear term, 1 for your coefficient of your differential term, derivative term, a p of x for that, and then whatever you wind up with on the right-hand side. Just go on and divide by it. Don't carry it around as a thing. If you can simplify, simplify. Okay. So there's the first one. Now, number 2. Okay. You've put it in standard form. Find your p of x. Okay. Now, what do you do once you found the p of x? Integrate the p of x dx. That's going to be some function. Integrate. Now, if that's not an integrable function, you're kind of dead in the water. There's not much you can do with it. But we're going to always assume and suppose, and I think it will be, that it's integrable. So don't carry around the integral, go on and integrate it. Once you found out what that is, raise that thing as the argument of your exponential function, okay? Now, again, don't carry around in integral form, whatever that came out being, e to the that thing then, okay? Now, don't mess with a constant when you do that integration. All right, that's step 2. Step 3, okay, my pen is wrapped, okay? Now, this is your integrating factor. You can call that your mu of x. That's a shorter hand. Multiply both sides, everything on both sides of the equation by that mu of x, okay? Okay, both sides, every term on both sides by mu of x. Now again, don't leave it as the mu of x. Multiply the things that you can multiply. If you can, factor things out or do whatever, do it. Make it as simple as possible. Okay? Now, when you do that, multiply both sides by that, stop and check. Okay, they don't say this. Stop and check and make sure the left-hand side is a perfect derivative. If you've done it correctly, it will be a perfect derivative. I always check and do. And if it is, then do your dx on the right and integrate the left. The left will just be the product of basically that mu of x. This is the 4th step. Write that as differential form. Okay? And then integrate both sides. If you've done it right, the left-hand side will be the product of mu of x times your y, okay? And on the right-hand side, it'll be some integral, evaluate the integral, okay? That's what you do. Solve for y by dividing by the mu of x, okay? A lot of blah, blah, blah on the words of it. A little bit easier to do it in practice. So let's take a look and do example 1, okay? Here's our equation. Solve this differential equation, dy dx minus 3y is equal to 0. Pretty simple equation. Now, number 1, I would solve this by separating variables, okay? Without a doubt, that's the way to go. But let's do that over here to the right-hand side, right? This is dy dx is equal to 3y, okay? Then put that in integral and differential form, and that would be dy is equal to 3y dx, and now divide by y, okay? This is separation of variables, okay? And then integrate both sides, okay? And this would be log y is equal to 3x. And take the exponential of both sides, and you can do a plus c if you want to. It'll pan out however you want it to be. I think yeah, let's do the plus c up here, and then you're doing either that. So this will be y is equal to, this is going to be, hopefully you'll see this. This is e to the 3x times e to the c, which is some other constant, and we'll just call that y is equal to c e to the 3x. Okay. Now, that's done by separation of variables. We know that's our answer. But let's do this according to the linear, because it is a linear function. dy dx is to the first power, y is to the first power. There aren't any products of those two. And this is already in standard form. The coefficient of the derivative is 1. That's exactly what they want. And it's pretty obvious, I hope, to you that the p of x is equal to 3, minus 3 actually, and the f of x is equal to 0. But who cares? Okay, you don't need to know those names. P of x is a little more important because what's the first thing you're going to do? You're going to integrate the p of x. Okay, so let me maybe take one more line to do that, not do it up here. Okay, you're going to integrate the p of x. So integral of minus 3 dx is going to be minus 3x. Don't do a plus c with that one, ever. Okay, leave that alone. That's minus 3x. That's your integral. And raise that to the e. Okay, e to that power. So e to the minus 3x is your integrating factor. That's your mu of x. You don't need to call it mu of x, but that's what it is. Now what you do with that, you multiply this by every term here. So this is going to be e to the minus 3x dy dx minus 3y times e to the minus 3x, okay, is equal to 0 because you multiply that by 0 and you get 0. Okay? Follow that? Now, this stage, pause and take a look. Is this a perfect derivative? Okay? If it is, it should be the derivative of e to the minus 3x times y, if that is a perfect derivative. Well, let's see. E to the minus 3x times y. I'm going to put the y in front. If that's a derivative of this, the first term will be derivative of the first, dy dx, times the second. Got it? Plus the second, the first, y, times derivative of the second, which is e to the minus 3x times a minus 3, and sure enough, that is. That is the perfect, this is d of this. Okay? That's your left-hand side. Well, this is 0 dx, okay? And if you integrate this, you just get y is equal to, y times e to the minus 3x is equal to some constant c, okay? And then multiply both sides by e to the 3x. Why? Because that then wipes this out, okay, or divide by e to the minus 3x, that's the same thing, so it'd be e to the 3x. There's your answer. Y is equal to c e to the 3x. A few more steps if you do the linear form, but it gives you the same answer. So always, if you can, separate the variables. If you can't, and it's still a linear equation, then you go through this procedure. Okay? Now, where is that valid? Value all values of x, minus infinity to infinity. Okay, let's try example 2. This is really boring talking to myself, but hopefully somebody will be coming in. This is a little more involved than the last one. It looks just like it up to a point. Dy dx minus 3y is equal to 6. Okay? Now again, this could be solved quite nicely by separation of variables. Okay? I'll come over here and do that real quickly. Dy dx is equal to 3y plus 6. Okay? And then separate the variables. Dy over 3y plus 6 is equal to dx. Okay? Write it in differential form, divide by the y term over there. Okay? Now, what is this? Let me write this as 1/3 dy over y plus 2 is equal to dx. Okay? Integrate both sides, and this is 1/3 the log of y plus 2 is equal to x. Okay? Then I would write this as log of y plus 2 to the 1/3 power, because that's the rule of logarithm. I think we talked about that before. Is equal to x. Oh, and when integrate, we probably need a plus c here, so let's not forget our plus c. All right. Then taking e of both sides. I'm running out of room at the bottom. So this is going to be, you take e of log, you get y plus 2 to the 1/3 power. And when you do the e, you lose the need for the absolute value. Okay? And this is equal to e to the x plus c, which really becomes some new c, e to the x. Okay? Because e to the x plus c is the same as e to the x times e to the c. E to the c is a constant. Put it out in front. Okay? Now, to simplify this a little bit further, cube both sides to get rid of the 1/3. You get y plus 2 is equal to some new constant c, because it's c cubed, e to the 3x. Okay? Because you just cubed it. And then you subtract 2 from both sides. Okay, and there's your solution. Okay, and they put in the book minus 2 plus c e to the 3x. Okay, now that works for that one. We know how to do it by separation of variables. Let's go back and do it by our linear form. Since it is a linear equation, dy dx is to the first power, y is to the first power, and there's no product of dy dx times y. Okay? So we're able to go. First thing we do, make sure that your coefficient of the dy dx is 1. It is. Next, locate your p, and it's the same as it was before. Your p of x was equal to minus 3, and then what do? You integrate the p of x. So you integrate minus, well, let's put the minus 3 here, dx. And that would be minus 3x. Okay? Done. Just as simple, just like we did before. Okay? That is, now raise that to the e power. Okay? That's your integrating factor, mu of x. You don't need to write that, but that's what it is. This is the thing we multiply by both sides. So we got e to the minus 3x dy dx minus 3y e to the minus 3x is equal to 6 e to the minus 3x. Okay? Multiply it by both sides. Then confirm that this is a perfect derivative of your integrating factor, e to the minus 3x, times y. It better be. If you did everything right, it should be. So let's see if that's indeed true. It's the first times derivative of the second, fine, plus the second, y, times derivative of the first, which is e to the minus 3x times a minus 3. Yes, that is a perfect derivative there, and that's equal to 6e to the minus 3x on this side. Okay? Well, change that to a differential form, and you integrate the perfect derivative here, and that gives you e to the minus 3x times y is equal to, integrate, well, ease up a little bit here. Integrate here, and what do you have? The 6 is out here. The antiderivative of e to the minus 3x dx is e to the minus 3x, and then you undo your chain rule type thing by dividing by a minus 3. Whereas if you take it a derivative, you'd be multiplying by minus 3. Here you divide by it. So this makes this coefficient a minus 2. Okay. Now, I think what I'm going to do is erase some of the stuff at the top over here because I don't have room. Okay. I think I can erase some of this at the bottom too because we use that to go elsewhere. I'll erase this. Okay. I want to leave my answer here. Okay. And erase this too. All I'm leaving is the answer. Y is equal to CE. Whoa! I erased too much. If my memory's right, it's e to the 3x. My eraser got out of control. Yep. Okay. This is our answer from before. So I'm going to leave that on here to see if we get the same thing. So carrying over, and I probably need to do a plus C here. Okay. Computer is doing weirdly today. All right. Now at this point, I want to multiply everything on both sides by e to the 3x. To wipe out this, it'll also wipe out this, and that makes it e to the 3x here. Okay? Now, what do we have? Y is equal to minus 2. That's all we got left here, plus c e to the 3x. And looky there, that's exactly the same thing we had there. I didn't have to erase everything, but perfectly fine. So sure enough, works both ways. Separation of variables, usually fairly easy, but linear, not too bad either. It takes a few steps, lots of steps, but if it's doable, the steps come out pretty reasonably well. Okay? Now, they do a little bit of talking about this. They draw the graph of that for various C's. And I think we may have a student. Oh my goodness. We do have a student.
I'm so sorry. I got 7:30. I was like snoozing.
You what? Oh.
Overslept.
Oh, okay.
I'm so sorry about that.
No problem. Did you lose power last night? Oh, you did? Yeah. I don't know when we lost it, but I got up about 4 something to go to the bathroom, and the nightlight was off. I thought, why is that? I thought the bulb must have gone. So I went to turn on another light. It didn't come on either. I said, oh no, we have no power. Well, the bathroom was totally black, okay, without any lights in it. There was no window. So it was, I said, this is going to be weird. Okay, and it was. But anyway, and by the time I left, still lights were off. What's that?
On or off?
Off. They were still off. Got up, that was, like 4 something, and I left right shortly after 7. So they were stayed off for quite a while. My wife said, Alabama Power was saying, they should be on by 11:30. So hopefully they'll be much sooner than that. Otherwise, we may lose stuff in the fridge and the freezer. I hope they won't. I don't know. My wife said it had been out a while. She's a fairly light sleeper, so she, I don't remember if she said what time she noticed it was out, but it was well before I noticed it was out.
I didn't even know it rained last night until I looked at my phone.
Yeah.
going outside.
Yeah. Had you close your garage door?
Yeah.
Good deal. Okay.
I only left it open like this crack for the dogs to get under.
Right.
And so when I did that, we got where our garage door is.
Yeah.
It's a low spot.
Yeah.
So
Yeah. Yeah. Well, my wife couldn't get into the garage this morning to get her car out because the power was off, so I had to go out and manually open the garage door because she has trouble doing that. So I did that. My car doesn't get to be in the garage because my side of the garage is now her stained glass studio. So my poor old car has to sit outside in the rain, but I don't have to worry. Okay. Let me get set up for a student to be in the room. And while I'm doing that, I'm going to down clear my head one more time. I'll be right back. I turned the projector off. It was a habit. I meant to turn I'll leave the projector on so you can catch up what I was doing. I meant to put the pause here. The old gray. Is that readable, or do I need to clean the board a little bit?
It's readable.
Okay.
It is under the dy over dx minus 3y equals 6. Is that you take
Okay,
the interval?
Okay. So yeah, you're up at the top.
Mm-hmm. And then below it, is that the interval?
Yeah, right. Okay. You aren't here to hear all this, so here going to. This is a linear differential equation. dy dx minus 3y is equal to 6. Now it's also separable. That part of the board, I had done it by separation of variables, but I needed more room, so I erased that and finished up. Okay, and we got the same answer. This is what I got from separation of variables. This is what I got. So this is a linear equation. Why is it linear? The dy dx is to the first power. The y is to the first power, and there's no products of either of those, so that's fine. Okay, now this is what we call standard form too, where the coefficient of dy dx is 1. And then here is what we call your p of x is the coefficient of the y. And this is a real simple one, minus 3. And that's just alpha of x. It's out there. You just do whatever you need to with that. So the first step to solve what they call a linear equation is to find that p of x minus 3. Okay, started to put the integration sign there. I did put it there and then decided not to, but I didn't erase it because nobody was in the room for it to bother. Okay, so you first identify that as your p of x, the minus 3. Whoops. Yeah, that worked too. Okay. Now, what you do with the p of x? You integrate it. Well, the p of x is minus 3, so it's minus 3 times the integral of dx, right? That's going to be minus 3x. Okay, first step, make sure it's in standard form. Yes?
Would it be 3x plus c?
Okay. On this integral, never put the plus c. All you're doing is finding what they call integrating factor. You don't care about the plus c. Normally, you'd be absolutely right. Okay? So this is that one. No, okay. So, yeah, on this one, never put the plus c. And I did that. So that's so once you integrate it's minus 3x, then you raise that minus 3x, that integral, make that the argument of the e function. So e to the minus 3x, that's your integrating factor. Okay? Now, what you do with the integrating factor, go back to your original equation and multiply that integrating factor, e to the minus 3x, times each term on both sides of the equation. So multiply dy dx by that, minus 3y times e to the minus 6, and 6 times e to the minus 3x. Okay?
Why don't we put it to e?
That's the rule. Okay? That's what you do. This is how you do these linear differential equations. Get it in standard form, meaning coefficient of this term is 1. Identify your p of x, which is the coefficient of your linear, the differential, but the linear. Integrate that without doing the plus c. Okay? Find out what that integral is, and whatever that integral is, do that as the argument of the e to the left. That's your integrating factor. then take that factor, e to the whatever it is, multiply it by every term on both sides. And this is where the magic happens. Okay? And here's what that magic is. You see what you've got here? That should be the perfect derivative of the product of your integrating factor, e to the minus 3x, times your y. It should be that. And I always have you go back and check. Okay? Okay, so let's just see if it is. If you took the derivative of this thing, it would be the first times the derivative of the second. Perfect. Plus the second, e to the minus, no, I'm sorry, y, times the derivative of the first. So the derivative of the first is e to the minus 3x, chain rule, times the minus 3. So sure enough, that is a perfect derivative of a product. That is a perfect derivative of a product. So since it is, write this in differential form, and don't forget, you still had over here your 6e to the, you have integrated this side too, so I just put the integral in there. And then put your dx over here, write it as a differential, and then integrate both sides. Well, you're integrating the perfect derivative. So that just gives you e to the minus x, y. Okay?
So, I'm at e to the negative 3x, I guess the one above it. We integrate, or like...
Okay, yeah. What we did, we verified that this was a perfect derivative. That this is the derivative of that product. Okay? And since it's a perfect derivative, then do your dx on the other side, and when you integrate that, you're integrating a derivative, fundamental theorem of calculus part 2. If you integrate a perfect derivative, you just get what's on the, see the integration and differentiation are inverse operations of each other. One undoes the other. So if you integrate a perfect derivative, you just get what's inside. E to the minus 3x times y. Okay? Well, you still got to integrate this side, and that's going to be 6 is out there.
Where did the y come from? Oh, is it from the dy dx?
Yeah, I mean, it was in the problem the whole time.
Well, no, like, what's it?
Yeah, see 3y, multiplied by the integrating factor, it was there. But then at this point, you notice this is a perfect derivative of that. Okay? Here the dy, if you integrate a product rule, it's the first times the derivative of the second, plus the second times the derivative of the first. And we went through that. Okay? So that confirms that's a perfect derivative. Since it is, integrate both sides here. You just have this on this side. Here you actually do the integration. 6 comes down. The antiderivative of e to the minus 3x is e to the minus 3x. Beauty of exponentials, right? But then you've got to unchain rule it. See, if you're taking derivative of that, it'd be times the minus 3, right? But since you're integrating it, it's dividing by minus 3. So when you divide it by the minus 3 here, 6 divided by minus 3 gives you a minus 2. So that's what that scratch is. Okay. And then you had your plus c. Okay. I've marked over this. That's this integration, you do a plus c. Or plus something. You don't have to call it c, whatever you want to call it. All right? Now, here you've got y. So all you have to do is multiply everything on both sides by e to the minus 3x. That wipes out this one. It wipes out that one. And it multiplies by that one. Okay? So what is your answer? Y is equal to minus 2 plus c e to the 3x. And there it is. Same as we got.
Is the formula we're putting it the d over dx e to the px dx y equals dx dx f(x)?
Say that one more time.
This formula right here, is that what you basically function into? The integral of px dx y.
see, the thing is, don't haul around that integral of p to x dx. Just integrate it. That's not what it is. Don't haul it around forever. And that's what we did. But that step that you just pointed out was this step right here. That, without the integrals in there, this is your e to the integral of px dx. That's what this is, times y. And that's a perfect derivative, okay? This is a perfect derivative up here. And that's equal to, what you had there was your integral of e to the integral of p to x dx. That's what this was, times your f of x. Your f of x here was just 6. So rather than carrying around all that notation, just evaluate what it is. Okay. And yeah, that's what you did. And then you integrated both sides of this. This gave you that product, and this gave you this. Okay. And then you multiply with that. I think there's another example coming up, so we'll do it. But backing off just a little bit here, they do say when the a sub 1, which is the coefficient of the derivative, and the a sub 0, which is the coefficient of the y, and the f are all constants, then this goes back to being one of those autonomous differential equations. There aren't any x's anywhere in it except there. And with that being the autonomous form, they say, and in this case it happens to be your y is equal to -2, that's this part here, that is your sort of the equilibrium point, but then from here, this is the one they say it repels, and I'm not going to draw it, but these are at various values of c. This is how this would look. Well, this is the repeller function, so when c is one value is up here, they really do a lousy job of explaining this. They just make it look like the mirror images here. They're not quite. They look awfully close to it.
It's a weird exponent.
Yeah. And it's expanded. I mean, it's what we call a repeller. Things are getting out of control further up.
It looks like it's getting unzipped.
What's that?
It's like it's zipper is getting unzipped.
Yeah, exactly. Okay. Yeah. Another way to look at it. All right. Now, and this answer we got is an example of a one-parameter system, and we call this in the general form of a solution, general solution. All right. Now, if you had an initial condition, then you zoom in on which one of those graphs you want to have. So then your form looks like this, dy dx. This is your standard linear form, plus some p of x dx. I'm sorry, p of xy. I'm so used to putting that as my integral. Okay. Is equal to some f of x. Okay. Basically what you were looking at just a minute ago. But if you know that y at x0 is equal to y0, in other words, you know a point somewhere out there, okay, x0, y0, then on your interval that contains that solution, that is your solution. You find that is the equation for it. So, say again?
This is going to be a hard test.
Has potential to be so. Speaking of which, how are the others coming?
I have just one question left on this.
Okay, on this one.
Yeah, it's number 9. It's taking
Right.
me a while to do.
Yeah.
But then the caliper one, I got all the hyperbolas and the
Oh, right.
name in
Yeah,
there,
right.
but I haven't gotten to the vectors yet.
Okay. All right. Okay, now that first 6 questions on the first page you don't have to do. That's optional, only if you just had plenty of time and wanted to work on those. We didn't go over those in class. That's the first part of chapter, what was it, 11? Yeah.
We started, I think, at 11.6.
Yeah, we start 11.6, and that is the part down there, those last 4. And then the next 2 pages, that's chapter 12. So that's the part you're talking about, the vector part. Okay, I thought you meant this vector part.
No,
Yeah.
sir.
Yeah.
No, sir.
Oh, yeah.
I was talking about the,
Right.
because I did the bottom of page 1. Because you said don't do
The bottom of page 1 is 11.6. Those 4 questions are just from there. Those are just filling in the blank, like you said. The next 2 pages, that's chapter 12. The top part of the first page is the first part of chapter 11, which we didn't go over. So that's why you don't have to do that.
Yes, sir.
And don't waste any time doing it if your time's of the essence. Focus on chapter 12
Yes, sir.
and 11.6. Yeah. All right. I just, because,
I got a free weekend this weekend, so I can get
Oh,
it
good.
done.
what, do you work a lot of weekends or?
I mean, sort of. I do kind of like under the table stuff.
Oh.
Like grass cutting and stuff.
Oh, I see. Okay, right.
I'm going to Florence.
Going to Florence.
That's what
Yeah, I know. Okay.
That's where I'm going to do. So.
Oh, I see. And you call that a free weekend?
Well, I mean, I ain't got to do anything.
Yeah.
I got a wedding to go Friday.
Oh, I see.
And then Saturday and Sunday. She takes physics 1 right now. She's got a final next week. So
Yeah.
she's got to be studying. It's going to be studying.
That's a year. Oh, okay. That sounds like a free weekend then. Okay. All right. Good deal. Let's do example 3 then. I think it'll help you to see one from scratch. You think?
Yes, sir.
Okay. Start from the beginning.
That was confusing.
Okay. So here we have the differential equation. X dy dx, okay, minus 4y is equal to x to the 6 e to the x. Okay. Now, right off the top, I'm going to make a bold statement here. I don't think there's any way in the world this can be a separable differential equation. Okay? So we have no way to check this answer. There's also no way in the world this is going to be an autonomous differential equation. So there's no way to use anything there. So basically, what we got to make sure, is it a linear differential equation? Well, take it.
Never mind.
No, what were you going to say?
Can we go ahead and move that? I don't know if I can solve that, but I was trying to get it in that standard form.
Yes, that's the next thing we're going to do, but I want to make sure it's linear. The dy dx is to the first power, the y is to the first power, and there's no products of those. So yes, this is linear form. And you knew that, didn't you? Okay? Now, what you're suggesting is exactly what we do next, and what do we do? And how do it? Just throw it away? Divide everything by x. All right? So what is our new differential equation? That goes away, and it's dy dx, good start,
Minus 4y over x.
minus, I would say 4 over x times y, because we want to write that as a p of x, okay?
So the p of x would be 4 over x.
4 over x, or minus 4 over x. The sign goes with it. And then the f of x becomes what?
X to the 5th.
E to the x. Perfect. That is a 5. Okay, all right. Now, just to keep it from being confusing, let me clean that just a tad. Okay. That's the form we're going to use. Okay? That's your standard form. What's the first thing you look for?
Your p of x.
P of x. And what is it?
Negative 4 over x.
Equal negative 4 over x. Perfect. Okay? Now, what do we do with that?
Integrate.
Yes. So we do the integral of minus 4 dx over x.
And it's just, that's ln.
That's ln. It's minus 4 times the log of x. Without a plus c, as you pointed out before. Right?
Yes, sir.
All right. Then what do you do with that integral of p of x?
We put an e.
Yes, you do that to the e. And since you're going to do that to the e, let's rewrite this ever so slightly using our well familiar
That's just
log
negative
functions.
4x.
That's what?
That's just negative 4x.
No, it's log of x to the minus 4. What? You don't remember those rule of logarithms? The whole thing about the slide rule and everything else? The log a times log of b is the same as log of b to the a. Take the coefficient and make it your x. That's only with logs. Don't do that with anything else. That's the property of logarithm.
4 is your a.
4 is the a. Minus 4 is the a.
A
A log b
log
is the same as log of b to the a.
x is the b.
Second,
X is the b.
x is the b. What's that? Okay. Now, why did I do that?
So we can put an e to it.
So, if we do an e to that, e to the log, those are inverse functions of each other. And e to the log of x to the minus 4 would be x to the minus 4. Yes, that's why we did that. Okay? So that is your integrating factor. I don't know if you remember, but that's what we were calling the muse of x. Okay? I don't know if it's beneficial to keep saying that, but I'm keep saying it. Okay. So what do we do with this?
Multiply everything in the original function.
Yeah, not the original, the standard form. Okay? So this is going to be x to the minus 4 dy dx. Go on. Minus
4 over x? No, wait. I don't know what you do.
It's the 4 you got right.
The 4 over x.
Okay. It's over x, but over x of what? Another way of writing this is 1 over x to the 4th. Is that going to help you any?
So it. Okay. So then 4 over x to the 4th.
No? Okay, you had 1x down there, and then you multiply this, so this will be x to the 5th, right? Times y, that was still there, remember? Okay. And then when you multiply,
Equals. Do we equal real quick?
okay, yeah, I'm sorry.
Wouldn't that just be xex?
X e to the x, right?
Yes, sir.
That's what I thought you said, okay.
I was saying e to the
I know what you said, okay. I was giving you benefit of a whole lot of doubt. Okay. Now, here's the deal. This left-hand side is supposed to be a perfect derivative, supposed to be the perfect derivative of your integrating factor, that's x to the minus 4 times your y. That's what it's supposed to be. Right? And if you've done everything right, that's what it should be. Okay? Do you understand?
Yes, sir.
Okay. So I always like to check it and make sure. Because if I made a mistake here, then the whole thing's going to be wrong. So let's see if this thing up here is exactly, the left-hand side is exactly a perfect derivative of your integrating factor, x to the minus 4 times y. So let's first do x to the minus 4 times the derivative of the second. It's first times the derivative of the second. That part's fine, right? Yeah, this is a product, right? You're taking the derivative of it.
Okay, so it'd be
The first side, first times the product rule. First times the derivative of the second, right? Plus the second, there's your y, times the derivative of the first. What's the derivative of the first?
minus 4 times x to the minus 1. Right? You reduce by 1 if you take the derivative. So there's where your minus comes from, your 4 and x to the minus 5. Yes, that is the perfect derivative. This is the perfect derivative of that. So I'll just rewrite that as that perfect derivative. Okay? And this is equal to x e to the x. That's your right-hand side. Your f of x now. No, well, whatever it was. To answer your question, it's magic.
I'm on board, alright? Like, I believe you. I'm 100% like there.
But you don't know why.
Yeah. I don't know why. So, how did you go from here to that? Like,
Okay.
what just made you go, what's this do? How did you know this was a perfect or derivative?
Okay. That derivation that we started last time and I finished before you came in this time, it had us do this, and then it said, and voila, this always turns out to be perfect derivative of your y times your integrating factor. It just does. That's why you did it.
So if I was going from here, I'd take that dx, dy over dx, take that y, apply it to here, and then basically always just do it like that.
Okay. If you've done it right, then this thing here, when you did that integrating factor, multiplied it by both sides, when you did all that, then what you should wind up on the left-hand side is a perfect derivative of the product of your integrating factor, that's why I keep saying it, x to the minus 4 times y.
It's always just times
It's always
y.
going to be that. If you did everything right, that should come out.
But it's always your integrated factor just times y.
Times y. Yeah. Okay. It should be. And that's why we did the integrating factor, so it would turn out this way. Okay? Now, I always like to go back and check and verify that it is right. And that's what I just did.
We didn't do the integral of the right-hand side.
We haven't got there yet. You're
Yeah, eager at the bit here, okay? So what I'll do now is write this in differential form, since I know that is the perfect derivative. I'll write this in differential form by putting my dx over here, right? Now I'll integrate both sides, okay? And the integral of a perfect derivative is the argument, x to the 4 minus 4 times y. That's it, okay? Now, I can tell this is one of your favorites. How do we do that integral?
Integration by part.
You are absolutely right. And how would you go with that?
Let's make the x the u value.
U equal x, I'll buy with that. And dv is equal to e to the x dx. Is that what I heard?
Yes, sir.
All right. Then the next part is du is equal to dx. Wonderful.
V is equal to e to the x.
E to the x. Nice. And then what do we do?
Plug and chug. So it's x times e to the x.
Yeah, x, e to the x is the first part, minus
The integral
of the bottom line here, right?
e to the x dx.
E to the x dx. And I think even I can do that one. So this is, let me write it over here, x to the minus 4y is equal to x e to the x, and what's the integral of e to the x dx? E to the x. You're good, okay? Now, here is what you put your plus c, okay? Now, what do you do from here? You're trying to, goodness gracious, this screen is doing crazy things. my screen just went black. Okay, there it comes. Okay, let's go this way. Okay, here we go. All right. What we're trying to do, I was trying to say, is isolate the y.
So we divide everything by x. No. Since x is technically on the bottom, we multiply everything by x.
X to the
4.
yes. If you multiply everything by x to the fourth, then x to the fourth times x to the minus fourth is just 1, right?
Yes.
Yes. So do this to x to the fourth, that'll make x to the fifth, right? By that? Okay. And this will be times x to the fourth, and this will be times x to the fourth. Okay? So these go out. And now we have y is equal to, I believe I'd like to just factor out the x to the fourth times
x e to the x minus e to the x plus c.
x e to the x minus e to the x plus c x to the fourth. Now that is a correct answer. Okay? Let me tell you what they probably did. They probably made this plus c out here a plus e to the c. And if they did that, no, I don't think so. Let me see. Let me see how they wrote their answer, so I'll try to, no, they left it just like that. Sorry. Okay. They did not do what I thought they were going to do.
Why would they make it e to the c?
If you tried to incorporate it with the other e's, see, every term over here had an e in it, and then you could have tried to, but that wouldn't have really helped. So I thought it might, but they chose not to anyway. Okay? So let's see. Their answer is just this one up here. They didn't. They duck. I don't know why that got the eraser in here. Okay. Their answer is this one right here. They didn't even bother factoring out the minus 4. Y is equal to x to the fifth e to the x minus x to the fourth e to the x plus c x to the fourth. Uh-huh.
What am I supposed to put in for answers if it's just...
I know, that's why I said the answer is your work.
And that's,
So I need to see that you're
is number
doing the
7
work.
pretty obvious I did the work?
You did some work, I'll say that.
Dude, this one was terrible.
I know, it was awful.
Dude, I was sitting there, I was like, how do I take the
Second derivative.
second derivative of 3 variables?
Yeah.
And so
Well, it's not 3 variables, 3 functions.
I had to go learn trig identities again.
Oh no, not that!
But hey, I know them now.
Good.
Because a lot of, like, to get sequent, I was like, man, how do I make this sequent? And I was like, I had to go back and do that.
Yeah.
I was getting, I got to a point, it was like sine over cosine times sine plus cosine.
Yeah.
I was like, this ain't right.
No, actually that sounded just right. But you have to do manipulations with it then. Get over least common denominator and do, and then the numerator becomes a 1.
How come now? How come when I was doing that, getting that least denominator, I felt like I was doing it right, but I felt like I was doing it wrong. Like I manipulated the sine x. I made it sine x squared, and then I made the cosine squared by multiplying it by the
Numerator and the denominator by
the
cosine.
denominator. But wouldn't I have to make the other side, like the y, the left-hand side?
No, okay. You're multiplying. Okay.
So like right here, you get sine x squared cosine over ln x cosine ln x. And I was like, okay, well, to add these together, they need to be the same denominator. So you get cosine squared over ln x. But I was like, wouldn't that
Okay. Well, no.
all you're doing is taking this term and multiplying by cosine ln x over cosine ln x. What is cosine ln x over cosine ln x? 1. Can you multiply by 1? Anytime you want.
Oh, see,
It doesn't change
I'm
the
just
value.
multiplying everything by 1 technically.
Yeah, but no, well, if you wanted to do that, you could, but you didn't have to. You just multiply this term by 1. It doesn't change the term.
Okay.
Yeah.
And then that works.
That's what we want to look at.
Yeah, I was tripping. And I was like, "Hey, Dad, can you does this look right?" He's like, "Dude, I don't remember that at all." I haven't done that since the 70s. I was like, "All right."
Since what?
Since like the 70s.
Yeah. Good deal. All right. So there was example 3. What you looking for? Okay. What are you looking for?
Oh, my paper.
Your paper.
My test paper.
What paper are you talking about?
Oh, the test paper.
Huh?
I thought I had my test paper under this.
I thought you did too.
That's weird. I was looking.
No. Oh, you got it.
Found it. Sorry.
Okay.
Crazy.
All right. Now, they have a little statement here. Except in the case in which the lead coefficient is 1, recasting of equation 1 into standard form requires division by a1 of x, which is exactly what we did here, right? First step that you did, remember? Okay. Now, when would that have been illegal to do? Divide by x. X was 0. You can't ever divide by 0, right? But if x was 0, then you don't have much of an equation, do you? Because this would be minus 4y is equal to 0. Okay? So y is equal to 0 would be a solution which wouldn't necessarily fit here, because I don't think you ever get y is equal to 0 solution here. Well, yeah, it would be if x is 0 only. But that's what they're saying here. That could lead to some singular points of the equation. They are potentially troublesome because by dividing by x, now you introduce a place where the function is not defined. Okay.
Is that saying like the question could give you like coordinate points?
Say that again.
Is that saying the question could give you like the y? I guess you give us the y x of 0 is equal to y of 0.
Oh, okay, yeah. Yeah, then if you had an initial value, then this would be, see, basically by doing that you introduce a vertical asymptote, right? Because you're dividing by x, so x can't be 0. Before that, x maybe could have been 0, though it wouldn't have been a very interesting problem, but it could have been 0, okay? But that would possibly introduce something that would be a problem. And we're going to see that in the next example as hard to do. This one, it wouldn't make any sense anyway, because if x was 0, then this would be, then y would have to be 0, yeah. And that would be what they call a singular point. But you see, this will never produce that, because x can't be 0 because you divided by it. So it's sort of kind of a moot point in this case, but in the next one you'll see it actually becomes more pertinent. I'll put it that way. Okay, so let's go to the next one, if you're okay with it. Are you?
Yes, sir.
Okay. Yeah, example 4. How are we doing on time? Good. Yeah. All right. Find the general solution of this one. Okay. But a timeout. I just remembered something I meant to do. I had said it at the very beginning of class. I had a pretty important announcement. But I said I'm going to wait till at least I get one body in the room. Well, a body showed up and I forgot to do it. Here's the problem, okay? At least by my wife's record, I have a doctor's appointment next Tuesday morning at 9 o'clock. So that means it takes about 45 minutes to get, if I were to come here, then I'd have to leave by 8:15 to be there at 9, and the class doesn't start till 8:30. So I'm not going to, if the appointment still stands, and they haven't called to verify it, but if it does, then we don't have class Tuesday. I know that's bad news for you, right? Sorry, get over it. Okay, but that's the second class we've missed. What I could do, I think the appointment will be over by 10. I hope so anyway.
Well, wouldn't it take 45 minutes to get back?
About 45 to get back. So we could start class at 10:45 or 11 o'clock or something like that. I don't have another class until 5 basically. So if you wanted to, we could just have a class later in the day.
That's all me.
Okay. You want to do that then? Shoot for 11. And if it looks like I'm not going to be back, the trouble is at the Kirkland Clinic, I can't send text, I can't send emails, I can't do anything because there's so much electronic stuff around the metal in the building, I can't ever get a signal there. So just what I would say is be here at 11. I hope I will be. If not, I'll get here as soon as possible. I don't anticipate any problem unless they're just running really late. My appointment's not going to take any time at all, okay? But it's just a follow-up. So I'm saying this for everybody listening in. I hope you're listening. Tuesday's class will be at 11, and if I'm not here right at 11, hang on. I'll get here soon after 11. We'll do 11 to, what would that be then? 1:15. Is that right? Yeah. Because we usually go 8 to 10:45, so that's 2 hours and 15 minutes.
10:45 minus 8:30, 2:15.
So it's 11 to 1:15. All right with that? Mm-hmm. Okay. Now we have to be out by shortly after 1:15 because there's class coming in here at 1:30. So we can't run too much over. Now we could have done this. No, we couldn't have done it for the last one because I had the eye operation. I wasn't going to be back here. So we want to go. We'll do that then. I'll try to put this out on Blackboard as well. I don't know if anyone's looking at Blackboard either, but I'll try to put it on Blackboard as well. Okay. I want to say that before I got carried away in this problem and completely forgot about it. Okay? All right. Now, what do we do with a problem like this? What do you do with a problem like Maria? Okay. First, is it a linear equation?
Can we get rid of the x squared minus 9 by dividing both sides?
Yes, that's a very good first step. Divide everything by x squared minus 9. Divide this by x squared minus 9. Okay? Divide that by x squared minus 9. Of course, that still leaves you 0. Okay? So, now we have dy dx is equal to x over x squared minus 9 times y, and that's equal to 0. Now we're in standard form, except I have an equal sign there, and that should be a plus.
Can we also rewrite x squared minus 9?
How would you like to rewrite it?
I mean, I don't know if it's beneficial or not, but I can tell that that's x plus 3x minus 3.
That's exactly what we would do next, yeah. Because what's the next step?
P of x?
Yes, and what is your P of x? That thing right there. And what do you do with the P of x?
It's regular the x's.
You what?
You integrate it.
Integrate it. And that's exactly how you'd want to integrate this. Integrate x over x plus 3 times x minus 3.
I don't want to do it anymore.
Yes, you do. You love doing this. You're so good at it.
I hate this.
No, you knew that right off the top. You had intuition to say, I want to do this anyway. See? You're just begging to do this. Weren't you? Yes. How do you do that?
Partial decomposition.
Yes, yes, yes. You're so good at it. So let's go over to the side here and say x over x plus 3 times x minus 3 is going to be something of the form of what?
It equals a x plus 3 and then b x minus 3. And then you can just rewrite it as a x minus 3 plus b x plus 3.
Okay, what were you doing?
Basically, you gotta cancel each other, cancel them all out. So a is gonna be a.
Oh, okay, I see what you're saying. Multiply everything on both sides by x plus 3 times x minus 3. You just got to the final thing, but then you would be wondering, I know I did that, but why? Well, I'm showing you why, because you're interested in that, aren't you? These go out, that one goes out, and that one goes out. So now we have x is equal to a times x minus 3 plus b times x plus 3. Okay? Now,
We try to solve for a and b, so I guess we'd plug in 3 for x.
okay, that's a great idea. Let's let x equal 3. So the left-hand side becomes 3 is equal to
0
right?
plus b times 6, so 6b.
6b. Okay, which implies that
b equals
1/2. Got it. Okay. Now we could do the same thing, except this time plug in x equal minus 3. And your left-hand side would be
negative 3
equal,
negative 6a.
right? Which implies that,
A equals negative 1/2.
really,
Or 1/2.
1/2. Okay, good. All right. All right. Now, that's a little suspicious, but let's just see. So what would our integrand be then? It would be the integral of, or 1/2 the integral of dx over x plus 3 plus 1/2 the integral of dx over x minus 3. All right, Daniel, let me pause a moment here in our work. By the way, we're on example 4. We're in chapter 2, first order differential equations. 2.3 is linear equations, and example 4 at the bottom of the page is general, coming up with a general solution, and that's what we're in the middle of. But I made this announcement just a little bit earlier. I'm going to make it again for your benefit in case you don't listen to the video now. I have a doctor's appointment, or at least it appears I have a doctor's appointment. See, this guy makes his appointments months ahead of time, and then later they'll verify whether it's still good or not. So I haven't heard the verification. But right now on the books, I have a doctor's appointment next Tuesday morning, this coming Tuesday, at 9 o'clock in downtown in Southside Birmingham at the Kirkland Clinic. No way I can be here. I'd have to, if I came here, I'd have to leave by 8:15 to be back there at 9 o'clock. So class doesn't start till 8:30. So hopefully the appointment will be over with by 10, and then if that gives me 45 minutes to get back here, then hopefully I'll be here by 10:45. And if so, we could start class at 11. Would that be okay with you? On Tuesday? What's that? Oh, you don't come on Tuesdays anyway? Okay. Okay, well then I guess it's not going to make any difference to you. So we will have class on Tuesday. It'll just start later. Now, if I'm not here at 11, I'll start as soon as I get here. Okay, but I have to be out of here by 1:30 because there's a class coming in here at 1:30. So. Second? Biology class, right? Yeah. So, anyway, we will start class later on Tuesday, but you're not going to be here anyway. Okay. All right. So here's our question. Now, I just want to, for funsies, check and make sure this is right. If I multiply this side by x minus 3 and that by x plus 3, then that's going to be x minus 3 plus x plus 3 and half and half. Yeah, that is one of that works out perfectly to be x. Okay, just want to make sure. Okay, now let's do that integration now. One half. I'll do that part. We're doing this one. Help me, help me.
I'll be honest, I won't.
Okay.
We can do it easier. We can make that x plus 3 x plus 3 is the -1. Raise it.
Okay. You could, or you could make that x plus 3 your u, and you'd have 1 over u du.
No, that's just ln.
That is all it is. So this is ln of x plus 3. That's it. That's all. Plus 1/2 ln of x minus 3. Right?
Yeah, I forgot about x plus. I forgot about the ln.
What's that?
I forgot you could always do ln.
Yeah.
Something over something.
Yeah. Okay. Now, if there were coefficients or powers and stuff, then you have more problems. But this is just coefficient 1, exponent of 1, so it's pretty
It's the
easy.
easiest answer ever.
Yeah. Okay. So what we're going to do, that is your integral. Let's see if we can clean it up a little bit. Let's look at this.
Yeah.
Okay.
We will- oh,
It's something to do, I must have a bad connection somewhere in there when I hit it. So this would be 1/2 times the log of x plus 3 plus the log of x minus 3. Okay? Something like that. Okay. Now,
we can't get rid of that 1/2. Oh, wait.
we will in a minute. I promise. Okay. What is the log plus a log is the log of the product. The sum of two logs is the log of the product. In addition to your trig functions, you need your log.
ln of AB. Like,
Yeah.
ln of AB.
Is equal to,
ln of A plus ln of B.
okay, so ln of A plus ln of B, that's the same as ln of A times B.
So ln of x squared.
Yes.
We're going back to our old function.
Yes, yes, yes. 1/2 the log of x plus 3, they should be absolute values, but times x minus 3. Okay? And then you do your, and you could write that, like you said, as your original function, and then make log of x squared minus 9 to the 1/2 power. Right? Then you do your next trig, log identity. Right?
Wait, did you write ln of x squared? Oh, it's raised to the 1/2 power because ln of.
Yeah, because it's a times log b, right?
Yep.
Yes, you remember that one well, don't you? Say yes, okay. Now, what do we do with that? Now that we finally got your 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 integral of p of x dx, what do we do with it? Yes?
Never mind. It's a minus sign. I was going to say we can just take the square root of that. If it was x squared plus 9.
Okay. You still need your absolute value bars. Okay, yeah. Because you see, yeah, that could be something else. Okay. But what's the next thing we do to it?
E.
E. All right. Take e to that, and e to the log is?
Cancel.
Yes. So it's x squared minus 9 to the 1/2. But again, and you're absolutely right, your x is limited now. X cannot be a number less than -3 or greater than +3. Because if it is, no, I'm sorry. X can't be between those two. Okay, if x is anything less than -3 or greater than -3 or less than +3, this thing negative. Yeah.
So if it was at number 1,
yeah,
the arrow's going this way.
Yeah, that's what you're dealing with here. You have to have x's this way or that way, nothing in the middle. And it's good that you notice that now. It's going to come back later. So this is your integrating factor, the mu of x. Okay? So what are we going to do? I don't know why that looks so weird, but it does. We're going to take our function and multiply it by it. So we're going to multiply by x squared minus 9 to the 1/2 dy dx plus, okay, now notice this one. It's the square root of x squared minus 9 in the numerator. In the denominator you have x squared minus 9, so this gives you an x times x squared minus 9 to the minus 1/2. Okay? I chose to write it that way. Times y, and that's equal to 0. Okay? Is that too confusing? I skipped a couple steps in there. What's that?
Nope. You just gotta do the hard stuff. You gotta do the hard stuff now.
Well, it shouldn't be too bad, because we hope this is the perfect derivative of your integrating factor, which is...
This is supposed to be a negative 1/2.
Okay.
On x.
Okay. This is your integrating factor. That's a positive 1/2.
Yeah, but up there.
Okay. Here?
Yeah.
You're asking if that is.
Yeah.
Okay, that's what I was asking. Did I skip too many steps there? I left out. Okay. What I did was multiply this thing, your integrating factor, by this side, right here. Right? That's perfectly fine. But now I'm multiplying by this. Well, this is x squared minus 9 to the positive 1/2 times this is to the minus 2/2 if you put it up here. Right?
Why is it minus 2/2?
Okay, it's in the denominator, that's why it's a minus.
Wouldn't it be just to the minus 1?
Okay. Yes, and is it 1 negative 2/2 minus 1 negative 2/2? 2/2 is 1. Yay or nay? Okay. All right. No, I think that way, and most people don't. So don't feel bad. Consider yourself lucky. You don't the same way I do. So, yeah. My wife will tell you, no, you don't want to think like that. Okay. Now, so this is you multiply by x to the 1/2 times the x to the minus 2/2, and that gives you the x to the minus 1/2, and then the x is still there. Okay. Now, the question is this the perfect derivative of a product of y times your integrating factor. Integrating factor being the x squared minus 9 to the 1/2 times y. Is that a perfect derivative of that product? Well, let's see, it's the first times the derivative of the second. Yes, that works. Right? Okay. You know what I've left off? No. Plus the second, y, times the derivative of the first. What's the derivative of the first? It's a 1/2 of x squared minus 9 to the times 2x. Well, the 1/2 and the 2 go out. Sure enough, that is. And this is to the minus 1. So yes, that is a perfect derivative of that. Which means, and this thing is equal to 0. Okay? So basically, what you have here is when you do a dx here and then integrate that, what you have is x squared minus 9 to the 1/2 times y is equal to some constant. Integral of 0 dx is just a constant, right? Derivative of the constant is 0, so the antiderivative of 0 is a constant. Right? Okay? So then what we do now is divide by x squared minus 9 to the 1/2. So y is equal to some c over x squared minus 9 to the 1/2 power. All right. Lots of steps, huh? And they wrote it as square root of x squared minus 9. Okay. Now, too much?
Yeah, it's getting a little migraine right here.
You what? Getting a migraine?
It's a little bit. I don't know why it's weird.
Sorry.
No, that's fine. It's a little straight. I don't know what it is.
You have migraines?
No.
Oh, okay. But you do have them occasionally?
No, not really.
Oh, really? Okay. Did you have enough sleep last night? I didn't think so.
Went to bed at 2.
Huh?
Went to bed at 2.
Okay. That's the problem. Was it chemistry or was it something else?
It was a little bit of chemistry, and then I couldn't sleep at all.
You need to start taking better care of your sleep time. Okay. Tuesday you'll be able to sleep in a little bit, but good.
Yeah.
Okay. All right. Anyway, that is the answer they have in the book. Okay. Now, you pointed out something that was pretty important. Your domain. Obviously, since you're taking a square root of this, your x squared, your x has to be somewhere out here, -3 or beyond, or somewhere over there, +3 or beyond.
So,
Okay. But, so again?
would the domain be negative infinity to -3 in unison?
Okay, it depends on what you put after the -3.
In unison, 3.
A bracket or a parentheses?
Yeah, I feel like it'd be close and equal. So that's close.
Except that if that was a -3, that makes this 0, and that's a denominator. So now you have to exclude even -3, right? And the +3. So it's values out here beyond -3, negative infinity to -3 in parentheses, and then parentheses 3 to positive infinity parentheses. Okay? Because this is in a denominator, you can't even equal 0.
So it'd be negative infinity to 3, and then unison.
Open parentheses 3 to positive infinity. Yeah. Okay. Now, here's the deal though. This thing of the plus and minus 3, you created that problem when you divided by that. Okay? Now again, if there were plus or minus 3 there, you would have wound up with an equation you would have either plus 3y is equal to 0 or minus 3y is equal to 0.
because if they were otherwise, so you have these singularities, like the x equal plus or minus 3. They are singularities. You introduced them when you divided by it, but I don't think they would have made a lot of sense in the first place. Okay? Okay. So anyway, they talk about those. You just exclude them because they can't be there. And now, how are we doing on time?
10:20.
Okay, we definitely have time for example 5. Any questions on this one before we move on? Okay. Example 5 is solve this one. dy dx, go back to they've already got it, plus y is equal to x. When y of 0 is equal to 4. Okay. Now, this looks so close to one we've done before, but it's not. Well, it sort of is. No, we haven't done it. We just mentioned it. Okay. I thought we had seen it before. How would you proceed? By the way, they pointed out where they did it before. Even though it looks really simple, it's not separable. Because you'd have to subtract y from both sides, and then you got x minus y. You can't separate those. They're not multiplied or divided.
You can't put a p of x.
You can't what?
Would the p of x just be 0?
Not 0.
1?
What? The coefficient of y. Is that what the p of x is? It's a coefficient function.
So
Here it's just 1. So yeah, you've just gone. Okay, first, this is standard form. Coefficient of dy dx is 1. We don't have to do anything there. Next thing we do is p of x is equal to 1. And then what do we do with that? Okay, I couldn't hear that.
I'm just writing things.
Oh, okay.
Take the intervals up.
Yeah, we take the integral of dx. Okay, and what would that be?
X.
X. Ooh, nice. Okay, and then what do we do with that?
Raise e power.
Raise it, yeah. So that's e to the x. Okay, that's your integrating factor, mu of x. Okay, so what do we do with that?
Multiply e to the x by everything. Multiply e to the x to everything.
By everything on both sides. That gives you e to the x dy dx plus e to the xy equal x e to the x. And then what do you note?
We did the perfect derivative.
We hope it's the perfect derivative of your integrating factor e to the x times y.
Y
Say again?
times y.
Times y, yeah. It's always what we hope that is. Let's check it and see. That would be the first, because this is the product, we'll do the product rule. First times root of the second, perfect, plus second times root of the first, perfect. So it works. And this is equal to x e to the x. So what do we do?
Interval.
Yes, we write it in differential form, take the integration, and that would be e to the xy is equal to the antiderivative of, the integral of.
We're going to do daggum integration by parts.
All right, good man. And what do we do? How do we do that?
U equals x.
U equal x,
X.
du and dv is equal to e to the x dx. Okay, next. du is equal to?
We're going to do x e to the x.
Okay, you're already there. v is equal to e to the x. Okay, so this will be x e to the x
minus this interval e to the x.
E to the x dx, and that would be x e to the x minus e to the x. Then you put your plus c. Been down this road before. And then what do we do? Let me write it over at the top here to make it easier to say. E to the xy is equal to x e to the x minus e to the x plus c.
Oh, we need to get the y by itself. So
Yes.
we divide everything by e to the x.
Divide everything by e to the x. Okay, now you have y is equal to x minus 1 plus c e to the minus x. I'm going to write it that way rather than write it in the denominator.
Now, it gave us y of 0 equals 4.
Okay,
So
that's exactly what we do now. That is a 4 there. So when x equals 0, y is equal to 4. So this will be 4 is equal to minus 1 plus,
I'm sorry. 4 minus 1 plus. Oh, it's wait. X equals 0. That's correct. Oh, it's just minus c.
it's a plus c, isn't it?
Was it a plus c? Oh, minus 0 is still 0.
Okay, good deal. All right. He's on the number line still. That's good. Okay. So what does that tell us?
4 equals -1 plus c. C equals 5.
5. Good. Okay. So let's go back and plug in. Y is equal to x minus 1 plus 5e to the minus x. All right. Now, just a little bit of visualization here. If you didn't have this in here, this last term, the e to the minus 5e to the minus x, this would be a straight line, slope 1, intercept minus 1, right? Now, because as x gets very large, this thing goes to 0, right? E to the minus 700 would be 1 over e to the 700, which would be an incredibly small number. So we're approaching, as a slant asymptote, you might say, not quite close to it, that is that line x minus 1. So this is a function that does that. And they show in the book which function this is. I don't want to draw it, so I'll refer you to the book. Here is the family of functions that would be this for various c's. When c is equal to 5, you pass through the point 0, 4. 0, 4 there, it crosses right there, and this is the curve. Like I said, for very large x's, you're approaching the line x minus 1, okay? But anything less than, they don't even have a good scale here, well they do. Anything much less than 4, then you're deviating from that. But anything beyond 4, you're awfully close to x plus 1, x minus 1. Okay? So that's the curve you're on, the one that passes through 0, 4. Make sense?
Yes, sir.
All right, good deal. So that was example 5. And by the way, that ce to the minus x, the 5e to the minus x, that is what they call a transient term. In the long run, it's not going to have very much impact. But in the short run, it has a big impact. So it takes it way off that line. But much larger values, it's...
By the way, you did to the negative x because you raised it, right?
Say again?
You made it negative for the c value. Originally we had the c divided by e to the x, and then you made it c e to the minus x. Is that minus x because you moved it up?
Okay. It's because right.
Look on the right side. Y equals x minus 1.
I'm trying to find where we're talking about. See here at this point right here. Oh, that one right up there. Yeah. See here we had e to the xy is equal to x e to the x minus e to the x plus c.
And then
right here. Then I divided by e to the x to isolate the y. So that was wipe this one out, wipe that one out, and this is c over e to the x is the same as c times e to the minus x.
Okay.
We move it upstairs. Yeah.
I'm making sure. I didn't know if that I'm pretty good at making stuff minus. I just didn't know on that one.
Yeah. Okay. Good deal. So that was example 5. Want to try to go for 6. Another initial value problem. All right. Solve this one. dy dx plus y, oh, jag, okay, plus y is equal to f of x. Okay? Initial value, when x equals 0, y is equal to 0. Okay? But there's an f of x there. What is f of x? F of x is a piecewise defined function where it's 1 anytime 0 less than or equal to x less than or equal to 1, and it's 0 anytime x is greater than 1. And it must not be defined for x less than 0. They don't tell us. Okay? Now, my gut feeling is they're going to take us through misery here. Okay. Let's go through and do. So this basically turns out being 2 differential equations. The first one is dy dx plus y is equal to 1. And that's any time x is between 0 and 1. Okay? Should not be a comma there. Should be equal sign. Okay? Or the other differential equation is dy dx plus y is equal to 0. And that's anytime x is greater than 1. Okay? So we really have 2 differential equations here. Now, I'll go through just like they do, and I'll try to find some reason to justify what they're doing. I don't think I'm going to find it, but we'll go. So, both of these are solvable by separation of variables. So I do not see why they're going to take us through I've lost my place here. Okay, here we are. Okay.
I guess they want us to do the whole thing, so let's do it. A lot of this, once we do it once, we don't have to do it again. So where do we begin? P of x is equal to 1. Pretty easy, and that's for both of them, so we don't have to do this but once. So the integral of P of x would be x, okay? You don't have to put a plus c, and this will be true for both of them. And then what do you do with the x? Yeah, okay, so it's e to the x is your integrating factor. That's your mu of x. And that will be true for both of these. Okay? Now, what do you do with that then?
E to the x times everything.
Okay, you multiply it. So that's going to be e to the x dy dx plus e to the xy is equal to e to the x. And on the lower one, it'll be e to the x dy dx plus e to the xy is equal to 0. Okay? Go back to the top, and what you notice here, or what you hope to be, that d of what?
Oh, e to the x.
E to the x times y had better be the left-hand side on both of these, and let's see if it is. E to the x times dy dx plus y times e to the x. Yeah, it works for both of them. So this is either equal to e to the x, or this is, I'll put my dx out here because I left it off there, e to the xy is equal to 0 dx. Okay? So, and the topper one, this will be e to the xy is equal to, what's the antiderivative of e to the x?
E to the x.
E to the x, okay? Plus c. Then we divide everything by e to the x. And what do we have is y is equal to 1 plus c e to the minus x. Okay? Okay? Okay. We'll come back to that in a moment. Down here, we would have, if you integrate both sides here, you have e to the xy is equal to some constant. So here you have y is equal to c over, or c e to the minus x. Okay. All right. Now, we have an initial condition. Y of 0 is equal to 0, so let's put in 0 is equal to 1 plus c, right? Okay, so what would c be?
C is just equal to negative 1.
Negative 1. So now your y is equal to 1 minus e to the minus x. And that's what they got to. Okay?
So what did you set it equal to? I'm sorry.
What's that?
Where did you set the c? Where'd you get that 0?
Okay.
Look at
Oh, okay. This is what we came up with. When we did this, the e to the x went out, this became a 1, and this became e to the minus x, right? Okay. So then I plugged in 0 for y and 0 for x.
Oh, okay.
Because that was my initial condition. Now,
this is where things get a little squirrely, okay? As if they worked before. You do not, or I can see no justification for plugging in x equals 0 here.
It would just be 0.
Yeah, well, that would be y. Yeah, if you put x, then you have 0 is equal to c. But why this doesn't make sense is this function, this is the only place where x equals 0 in the system. So that's the only place where it makes sense to plug in x equals 0, because this is where that's defined. Now what you plug in down here is the fact that you want this function to be continuous. The derivative won't be continuous, but you want the function to be at x equal 1. Well, at x equal 1, plug in here, there's the function. At x equal 1, you have y is equal to 1 minus e to the minus 1. Okay? So at x equal 1, y is equal to 1 minus e to the minus 1. Okay? So that's what we plug in down here as our implied other condition, is that for the one down here, when y is equal to 1, even though this isn't defined for y is equal to 1, we still want it to connect there. So we'll have 1 minus e to the minus 1 is equal to minus, no, this is a different c. Let's call it c1 or something like that, e to the minus 1. Okay? That's ugly now. Okay. All right. Now, let's multiply both sides by e, and you get e minus 1 is equal to c1. So that's your c1, and this will be y is equal to e minus 1 times e to the minus x. Okay? And that will be for all x's greater than 1. Okay? That's where that comes from. You don't use the same c's here. This c is only valid for here because that's the only place where x can equal 0. So this initial condition is only good there. Now, this equation is still good for beyond 1, but because we want it to be equal, we don't want a discontinuity at 1, then we find out what the value of that one is at 1. That's 1 minus e to the minus 1, and plug that in as our sort of another condition, is that when y is equal to, when x is equal to 1, okay, y is equal to that. And that gives, plug that in here, and that's what it comes out. So it's a rather strange problem, and they do have a little picture of it, which shows how really strange it is. This is your differential equation. The y dx is equal to 1 anytime you're between 0 and 1, but it's 0 everywhere else. Okay? Well, then the function that tells you that is this one. Here is the part where it's 1 minus e to the minus x, and then here's the part here where it's the rest of it. Now, and that's what. So the reason we went through all that is so they would be at the same value here. We didn't want the discontinuity here. So the first derivative is discontinuous by a long shot, but, or not the first derivative, the y value is. But this needs to be continuous. That's what you get. Not much of a function, but it does fit right. All right. How are we doing? Oops. We went over. But guess what? There's no extra charge, so you can rest easy. Second? Yes. I'm going to give you that to you now. I do want to move my mark here so I'll know where to pick up next time. We're going to talk a little bit about the error function next time. So that's all they're going to do is basically talk about it. I'll have one example. So exercise set 2.3, do any of the odds 1 through 23 that are in the back of the book. I think most of those will be. Then do any of the odds 25 to 35. I think most of those will be in the back of the book. Then you can try some of 37 to either 37 or 39. Those are, again, discontinuous functions at the end, just like the one we just did. And 41's the same way if the answer's in the back. Stop there, because after that you get into the error function, and we haven't done that yet. All right, good deal. See, today we started in, did we start in 2.3? I think we did. Yeah, we started in 2.3. So today is just 2.3. Good deal. I hope you have a good weekend. Remember, Tuesday's class starts at 11, or as soon as I get here after 11.
Yes, sir.
Yeah.
See you then.
All right. Take care. Have a good weekend.
Early?
What's that?
Did you guys leave early last Thursday, or did you not come here last Thursday?
Okay, last Thursday I had an eye surgery.
Okay, just making sure.
Yeah. And I announced it in class. So if you listened to the videos, you would have heard me say that.
I don't think I was actually in your class by that time.
You've been in the class for quite a while.
No, I mean like actually in the class.
Okay. No, okay. You came that first day, you weren't listed in the class. Ever since then, you've been listed in the class. Yes. And listed as paid even. So, yeah. So, I need to get some work from last term. Okay. And have you already got the first test from this one?
Yes.
You did, okay. So, don't get further behind.
Yes.
Okay. Yeah, but I had eye surgery last Thursday, and I had announced it the Tuesday before, probably the Thursday before that even. So it had been out there for quite a while. Okay. Sorry that you didn't get the word. Huh?
I said okay, and good luck with your Tuesday appointment.
Yeah, okay, thank you. Appreciate it.